Hi, everybody, and welcome to the section on 16.4. This is the section about expected value or expectations. And in this section and the next, we're going to build on what we did in section 16.3. So in 16.3, we defined what probability was, and we looked at several examples. 16.4 and 16.5 are applications of 16.3. So it's difficult to describe what expected value is without just showing you some examples. So let me just dive right into this. Here's a first example. Suppose you're in some guy's class, Professor Goody. You're in his statistics course, and the grading for the course is based on 2 midterms, homework, and a final exam. The breakdown for scoring is given as in this table. So this is like a snippet from his syllabus. The 2 midterms are both worth 20%, the homework is worth 25%, and the final exam is worth 35%. Suppose that each of the midterms is worth 100 points, the homework is worth 200 points, and the final exam is worth 200 points, and these are your scores. You got an 82 on the midterm, an 88 on the midterm 2, 182 out of 200 points on the homework, and 190 out of 200 points on the final. How do you calculate your grade? Well, this is something you've probably done in many other courses, but you do what you sort of think you should do. This is an 82% right here, 82 out of 100. That's what you got on midterm 1. You got an 88% on midterm 2. On the homework, you did not get a 182%. Right? You got 182 out of 200. Well, 182 out of 200 is a 91%. So you got a 91% here in this homework column. And finally, in the final exam column, you got 190 out of 200. So this is not 190%. This is a 95%. So you have an 82% here, and that 82% is worth 20% of your grade. You got an 88% here, and that was worth 20% of your grade. You got a 91% here, which is worth 25% of your grade. And you got a 95% here, and that is worth 35% of your grade. So when you calculate your grade, you basically just take 20% times what you got here, plus 20% times what you got here, plus 25% times what you got here, plus 35% times what you got here. And that's where this equation down here comes from. 0.2 is 20%. So this 82 score is 20% of your grade. So 20% times 82. And then this 88% is 20% of your grade. And then this 91% is 25% of your grade. And then finally this 95% is 35% of your grade. So when you do all the addition here, you end up with a 90%, which is an A, or in our case, an A minus. So again, I hope this is something you have done before. This is how you will calculate your grade in this course. Of course, this doesn't reflect exactly how our course works, but you will essentially compute a weighted average like this. So notice that, so this is an 82, 88, 91, 95. Notice that down here we did not just take the average of those 4 numbers, right? We did not do 82 plus 88 plus 91 plus 95 and divide all of that by 4. We did not do that. Why didn't we do that? I mean, these are our 4 grades, right? Our 4 grades are the 2 midterms, homework, and final. Why didn't we just average those grades together to get our overall grade? Why did we do this weighted average here by percentage? And the answer is because homework is worth more than the midterms, right? And the final is worth more than anything else. So if you just take a straight up average, you are assuming everything has the same importance, that the final exam is worth the same as the midterm. But that is not true. The final exam is worth almost double what the midterm is worth, and that's why you have a 0.35 here versus a 0.2 right there. So this is an example of a weighted average. And here's the formal definition. A weighted average computes an average of a given data set, but it weights things by how important they are. So suppose that we have these outcomes. So in our previous example, we have x1, x2, x3, and x4. So this list here only has 4 things in it. And x1 would be an 82, x2 would be an 88, x3 would be a 91, and x4 would be a 95. Each of those numbers has a weight, and the weight is given by the grade distribution, right? This 82, its weight was 20%. This 88, its weight was also 20%. This 91, its weight was 25%. And this 95, its weight was 35%. So don't get bogged down in the formalism here. All we're saying is that we have several options. We have several values, and in the previous example, grades. Each of those values has a weight, and the weighted average is simply take the value times its weight, plus the next value times its weight, plus the next value times its weight, and so on all the way until you finish. So you have value times weight, plus value times weight, plus value times weight, plus etc. until you're done. And that's exactly what we did here, right? Value 82% times weight, value 88% times weight, etc. That's what a weighted average is. Okay, so now let's move on and talk about expected value. This example I'm going to give you now is a motivating example for expected value. Expected value is an application of probability, and in particular, it's a kind of a weighted average. So that's why when I give you the definition of expected value, it will look very similar to this. So this is sort of motivation for what we're going to do. Okay, I think that most of you probably took the ACT. I am from Texas, so I took the SAT. So this is very familiar to me. I don't know how familiar it is to you. But just in case you don't know, in the multiple choice sections of the SAT, each question has 5 possible answers, A through E. A correct answer is worth 1 point, and to discourage guessing, an incorrect answer carries a penalty of 1/4 of a point. So if you get a wrong answer, you will lose 1/4 of a point. So that means that if you miss 4 questions, you've now lost a full point. Imagine you are taking the SAT and you're facing a multiple choice question for which you have no clue as to which of the 5 choices might be the right answer. They all look equally plausible. You can either play it safe and leave it blank, or you can gamble and take a guess. In the latter case, the upside of getting 1 point must be measured against the downside of the penalty. Right? So your upside is a point, your downside is negative 1/4 of a point. So what should you do? Should you guess or not? Or does it not matter? How would you answer this question? Well, we're going to answer this question with expected value. So we're not going to call it that yet, but that's what we're going to do. So notice that if you're randomly guessing the answer to this multiple choice question, you are actually conducting a random experiment, if you like. And the sample space of that experiment are just the 5 options for the question. So this is assuming you guess, right? If you guess, then leaving it blank is not an option anymore, right? You are randomly guessing, therefore these are the 5 options that are the result of your guess. Since each of the 5 choices is equally likely to be the correct answer, you assign probabilities of 1/5 to each outcome. So in other words, A is correct with probability 1/5, as is B, as is C, as is D, as is E, right? You have a 20% chance of each one of those being correct. Okay, so when you think about what kind of payoff you get when you answer this question, you either get 1 full point or negative 1/4 point. So for the sake of argument, let's just say that B is correct. Okay, we don't know that B is correct, but that's just background information, right? Let's just assume B is correct. The logic will follow no matter which one of these answers is correct. So if B is correct and you take a guess, you get 1 point if you've guessed B. And the probability of guessing B is 1/5, right? 1 option out of 5. If you guess any of the other four, your point payoff is negative a quarter of a point, and you're going to get that payoff with probability 80%. Right? So there are 4 out of 5 wrong options. So if you just guess, you have an 80% chance of losing that quarter point. So now let's take that and use it to define expected value. So suppose we have these numeric values. And so in this case, the values are these payoffs. We have a 1 and a negative 0.25. Those are the possible payoffs we could get by answering the question. Each of those payoffs has a probability. The expected value is given by this formula. Value times its probability plus value times its probability plus etc. all the way until you're done. So notice that if we just replace a P here with a W, then we get exactly this. So expected value looks just like a weighted average, except the weights are probabilities now. But otherwise it's the same idea. You take value times its weight, value times its probability, and add. Okay, so here we have, in this case, we'll have one of the payoffs was 1 point, right? That's if you get the question correct. And that has a probability assigned to it of 0.2 or 1/5. And then the only other option for us was negative 0.25, negative a quarter of a point. That had probability of 80%. So when we compute the expected value, we get 0.2 times 1 plus 0.8 times negative a quarter, and those cancel each other out, and you're left with just 0. So in this case, we get an expected payoff, which, if you like, expected value, since we're dealing with payoffs, you can say expected payoff. Your expected payoff in this case is 0 points. So what does that mean? The fact that the expected payoff is 0 means that this guessing game is fair, if you like. So over the long run, the penalties that you would accrue for wrong guesses are balanced out by the benefits that you get for your lucky guesses. So this knowledge will not impact what happens with an individual question. The possible outcomes are +1 or negative 0.25. But it does give you some strategically useful information. On the average, totally random guessing on multiple choice questions of the SAT doesn't help you or hurt you. So I suppose you could take this as, well, just guess away, So the fact that this expected payoff is 0 points, remember, if you leave the question blank, you also get 0 points. So in the long run, if you do this lots and lots of times, if you guess lots and lots of times, your penalties will just balance out with your benefits. So if you're going to guess a lot, that's basically equivalent to leaving a bunch of questions blank. Okay, so we're going to look at some more examples here, but the key thing to take away from this is the phrase in the long term or in the long run. So when you're taking the SAT, if you only guess on, let's say, 6 questions, that's not very many, then who knows what might happen. You might get lucky on all of them and get a payoff of 6, right? Or you can get all of them wrong and get a payoff of negative 1.5, or anything in between. In the short run, if you're only going to answer 6 questions, we have no idea what will happen, okay? Expected value and probabilities in general don't tell you anything about the short run, about doing things twice or 3 times or 4 times. But if you guess hundreds of times, dozens of times, then yeah, you would expect your benefits to balance out with your penalties. So this 0 points here, this expected payoff being 0, that's a statement about doing things over and over and over again many times, not twice, not 3 times, whatever. Okay, now, okay. So one thing I forgot to include in here is, let's think about the situation where, okay, we're taking the SAT, right? We have 5 options. Suppose you know that option A is wrong. Okay, you can eliminate one of the answers, and now you're left with 4 other answers. In that case, think about the expected value. What would happen in that case if you just guess, right? So A is gone, and each of the other 4 you have no idea, right? So you're going to assign probabilities of a 4th to each of these, because there are 4 left. So imagine this A column is just gone, right? Now you have 4 questions left. Now your probability of getting a question right is 1 out of 4, not 1 out of 5. And so now in this formula here, you'd have 0.25 times 1, because now you have a 25% chance of getting something right, plus a 0.75 times negative 0.25. Okay, so what is that? Let me just do it here. Oops. Not my calendar. There we go. Okay. So 0.25 times 1 is, of course, 0.25. Now you have to do plus 0.75 times negative, oops. Sorry, let's start again. So 0.25 minus 0.75 times that quarter. That gives you 0.0625. Okay, now notice that this number is positive, right? The original expected value was 0 when we had 5 options and we were guessing among the 5. But now, if we know that A is wrong, and we're now guessing amongst 4 guys, now we get an expected value that's positive. So that means that if you're going to guess, and you can eliminate one of the options with confidence, then in the long run, your benefits will outweigh your penalties. Okay, so the fact that this is positive means that that's good for you. So if you've ever taken an SAT prep course, sometimes they'll tell you that if you can eliminate one or more options, you should just go ahead and guess, because in the long run, that's a good strategy for you. Now, if this number were negative, that would be bad for you. You shouldn't guess, but in this case, we got something positive. Okay, oops, don't know why it does that. Okay. So I want to do one more example, and I want to really hit home what expected value means. So consider the random experiment of throwing just one die. Right? So when you throw a single die, there are 6 options. You can roll 1, you can roll a 2, 3, 4, 5, or 6. Each of those options is equally likely. So 1 has a probability of a 6th, 2 has a probability of a 6th, 3 has a probability of a 6th, etc. So if you do 1 times its probability plus 2 times its probability plus 3 times its probability, etc., you get a number of 3.5. Okay, so what does that mean? What does that number mean? That means that in the long run, the average die roll will be 3.5. So it's hard to really see what that means unless you actually do some dice rolling. And so, you know, I'm not physically in front of you and I don't have a physical die with me, right? So instead what we're going to do is I wrote a program that just simulates dice rolling, and it will tell you what the average dice roll is. So I'm going to tell the computer to roll a die 3 times, and I want to see what those values were. Okay, 1, 5, and 6 is what were rolled. It rolled a 1, then a 5, then a 6. So the sum of those dice was 12, right? 1 plus 5 plus 6 is 12. The number of times you rolled the die was 3. Therefore, the average dice roll is 4. Okay, you just average these die rolls together, right? So you see how this works? The average roll of these 3 dice was a 4. Okay, so let's do this again. Let's roll 3 die again. Okay, this time the average was 4.3333. Let's do it again. This time the average was a 2.6667. Okay, so let's just review what happened here. The first time I rolled the die 3 times, I got a 156. That resulted in an average roll of 4. The next time I rolled the die, I did a 535, which resulted in an average roll of 4.333. Right, that's the average of 5, 5, and 3. The next time I did it, I rolled a 1, 3, and a 4. And now the average roll was a 2.667. Okay. So these numbers are kind of all over the place if you think about it. We're ranging from 2.7 to 4.3. When you roll a die only 3 times, that's a short-term thing. You know, who knows what happens in the short term? Maybe I'm going to roll 3 6s, and then the average roll would be a 6. Or I could roll like a 1, 1, and a 2, and then the average roll would be like a 1.3. Okay, so who knows? But now let me do something different. I now want to tell it, I'm going to roll the die 10,000 times. Okay, that's a lot. All right, way more than 3. I'm not going to have it show me the rolls because I don't want it to display 10,000 rolls. So I'm just going to skip past showing the data. Okay. It says here the sum of the throws was 34,940. The number of times you rolled the die was, of course, 10,000. That's what I told it to do. And this sum divided by this number of rolls is 3.494. Okay, so let's roll again. And let's again do 10,000. I don't want to see the data. It's too much. 34882. And when you divide that by 10,000, you get 3.4882. Okay, one more time. 10,000 rolls? No. 3.491 is now the average. Okay. So notice when I rolled the die only a few times, 3 is a very small amount of times. Notice that the average roll, those numbers were all over the place. 4, 4.3, 2.7, etc. Notice though, when I roll the die lots and lots of times, 10,000 times, these numbers are not all over the place. They are all essentially 3.5, which you'll remember is the expected value. That was the expected die roll, right? That's what we got. 1 times its probability plus 2 times its probability, etc., was 3.5. So this is literally what a expected value is giving you. In the long run, if you're going to do an experiment lots of times, and 10,000 is certainly lots of times, you should expect that your average value is extremely close to your expected value. So let's just do this one more time, and let's roll a die like 50,000 times and see what happens. No, don't show the data. 3.49392. Okay, so we're getting even closer to 3.5. So if I were to roll the die billions of times, I would expect to see something like, 3.4999992 or something, right? So notice the more times you do this experiment, the more predictable the average becomes, right? So just for emphasis back up here, in the short run, we really had no idea what to expect the average roll to be, 2.7 all the way up to 4. But the more times we roll the die, 10,000 times, 50,000 times, the average die roll becomes extremely predictable. It becomes something very close to 3.5. That's what expected value is telling you. In the long run, what's the average I should see, right? What's the average value I should see? So, oops. So in this example here, the average die roll should be about 3.5. In this example here, where I had 2 possible payoffs, either 1 or negative 2.5, my average payoff ended up being a 0. So in the long run, as you guess and guess and guess on these SAT questions, you should expect your average payoff to be 0 points. Your benefits outweigh your penalties. Here, if you think about a die roll as a payoff, your average payoff is 3.5. And basically what that means is these 1s, 2s, and 3s are sort of balancing out with these 4s, 5s, and 6s. Right? So basically, if you roll a die 10,000 times, basically for every 6 you see, you'll also see a 1. For every 2 you'll also see a 5. For every 3 you see, you'll also see a 4. So all that balances out right at this tipping point of 3.5. Okay, so that's the idea of expected value and expected payoff. If in your homework you're asked about expected payoff or expected value, what you should do is you should build a table like this on a piece of paper. You should list your payoffs, which in this case there are only 2 of them, but you can imagine there might be more depending on the context. So list your payoffs, then list the probability of each payoff. So in this case, the payoff was 1, and its probability was 1/5. And the other payoff was negative 0.25, and its probability was 0.8. Once you have this table in place, all you do is you multiply down and then add over. So multiply, add, multiply, add, multiply, add, multiply, however many columns you have. So in this case, there are only 2 columns, and we ended up with just this multiplication. Okay, so hopefully that illuminates the concept of expected value. And as always, you should contact me if you have questions.